Starts with the scientific contents. I will just give a few pieces of information about the program tonight. We got quite far in the conference. Tonight we have the banquet, and I will say a few words about that. Tomorrow we have the excursion to Asta Zero, and at the closing I will say a few words about that tomorrow. So, the banquet, to remind and tell newcomers, on the back of your badge you can see if you are registered to the banquet, and many of you who will not join the banquet have been nice and told the registration desk so we can offer places to those who don't have tickets and want to join. So if there are any more who cannot join, please let them know at the registration desk. And don't forget the badge, that's the entrance ticket. Okay, boats depart from the Riverside Hotel, and that's over there in that direction. They should leave 18 sharp, but we are many, so as soon as one boat is full it will take off. So you could, if you're ready, you could drift in that direction a little bit before 6 o'clock also. If you don't want to go on the sightseeing boat ride, you could also take a bus over there or walk, but please be there by 7:30. To return, we have boat trips back also, but it will go straight away at 11 o'clock, first possibility, and the second possibility at 20 to 12. But you could also return anytime you like by take a regular bus or a regular boat or walk. You have the information in the app under social activities here if you want. So the boat looks something like this, and you see that we managed to make the weather like in the picture. If you want to walk, we are here now, and there is a shortcut, a pedestrian bridge here, and it here says it takes about 28 minutes. So if you need less or more, you can contact them and say they should correct it. But that's the distance. You basically more or less just follow the shore. So apparently it's not an efficient way to walk over here, but to cross over here. And the boat stop is here, so you can also take a regular boat back, which stops here. And we hope it will be a nice evening. You will have a lot of fun, but don't forget, tomorrow morning we give you a quarter of an hour extra to sleep. But at 8:45, Jerome Plog will speak about iGame, the competition they had in the Netherlands, I think it's 2 weeks ago, and the results from that. And that will probably be very interesting, so don't miss it. With that, I leave the word to the chairpersons.
Thank you. My name is Sergiu Nedevski from Technical University of Cluj, Romania, and together with Joachim Thursted from Volvo Car Group, we will chair a regular session having the title Mapping and Localization. The first paper will be presented by Frank Schuster from Daimler, having the title Robust Localization based on radar signal clustering.
Thank you for the kind introduction. I hope you can all hear me. My name is Frank Schuster, and I'm going to be talking about robust localization based on radar signal clustering. And yeah, just to give you a short overview of what I'm going to be discussing today. So after a motivation and describing my sensor setup, I'm going to be talking about the localization algorithm presented here, namely the cluster map representation that I'm using for the radar data and the map update functionality, as well as I'm going to be showing some results, and I'm going to summarize and give some future work. Please, for further discussion, also join the poster session in the afternoon, at 1625. It's upstairs in the hall. So motivation, we have a scenario which is kind of which is something like this. We have a parking lot, and the vehicle must localize itself on a previously self-recorded map on this parking lot using radar sensors. So the difficulty with this is, so you can see a lot of parking areas here where the cars can just park anywhere they like, basically, and it's difficult to make the vehicle localized despite the changing conditions. And also another aspect was to use as little memory as possible. So let me talk a little bit about the sensor setup. You see our test vehicle here depicted here. We have 4 radar sensors, each with an opening angle of 150 degrees, and wheel encoders for odometry, as well as a yaw rate sensor on the ESP for odometry input. And the ground truth that is only being used as a reference here is acquired by a DGNSS INS deeply coupled system. Okay, so let me show you what the raw data looks like. So here you can see the raw data that is referenced by the ground truth, and you can see here that the parking lot is basically depicted by areas of very high density here, which actually corresponds to physical objects, but there are very many points of radar data that just don't belong to any physical objects, and which are located here and here, that are just noise from scattering or from other effects like interference. And to cope with this, we came up with the cluster map representation. So the radar data by itself is too noisy to perform any kind of scan matching or anything like that. So the cluster map representation is accumulating data over time and then uses that to perform scan matching. So if we consider just one radar point right here, we can define maximum radius around this point and say, okay, this is the maximum size a cluster is supposed to be. And then we look at all the other points that are measured around this point, and we can see that if the density is very low, we call this an outlier microcluster or O microcluster. And if the density exceeds a certain limit, then we call it P microcluster for potential microcluster. And also, the following properties are assigned to the cluster map representation, which is basically the cluster weight, which is basically proportionate to the density of the cluster, so the number of points inside this radius divided by the surface area. Then we have the mean point, the mean of all the points, which is the cluster center, and that is basically describing the position of the cluster in our scan. And then we also have a radius, which is just a standard deviation, so you can look at this like a two-dimensional Gaussian distribution. This algorithm was proposed by Cao et al. Actually for data mining purposes. We applied it to the radar data. So let's look at one of the scans a little bit more closely. So you can see here a cutout from the previously shown picture, and you can see those cluster points and also here those high density areas. And if we apply the clustering algorithm, you can see that most of the clusters are located where the density is very high. And if I remove this, if I remove the raw radar data, you can see this even more clearly. Okay, so what do we do with this now? So we have a particle filter-based SLAM approach with a control update function using the odometry information. So the particles are being distributed using odometry, and the measurement update comes from scan matching between the clusters. So we can look at this way. We have radar and odometry incoming. The radar targets are being clustered, and then in the scan matching process, for each particle compared to the map, and then a map update of the particle is performed, and the odometry information, namely the velocity and the yaw rate, are used to update the particle filter. Okay, so I talked about P and O microclusters, and P microclusters are used for the scan matching, and so what about the O microclusters? Why don't we just throw them away and say, okay, that's all noise, we don't need that? Because we can do something nice with this, is map update. And the map update is basically done via, I call it density decay for now, which is, you remember the formula of the particle weight, of the cluster weight, which is the number of points inside that Rmax circle. And we can reduce each time step, we reduce this weight by a certain factor beta, and by that we kind of decay the cluster. And if we have a P microcluster, so a cluster with high weight, it can, if it's not observed anymore, then it's going to be eventually degraded into an O microcluster and not longer be used for localization. On the other way around, we can have an O microcluster, and if it's measured at a higher rate, then there is the decay. Then the O microcluster will eventually be promoted to a P microcluster and be used for position update. And this way, we can perform a map update functionality. And this is depicted in this short video. So here you can see in the center that this tear-shaped symbol represents the car with the heading showing indicated by the tip. And you can see a bunch of objects in the map here. These are all cars. And I'm going to go along and describe what you can see here. So if I start the video, you can see that here, this car, this is also a car. Trust me, if you look at these maps long enough, you see cars everywhere in these point clouds. And you can see that this is not a very distinctive car shape here, because the angle of this line is off. So if the car passes, you can see how this is updated, and more points are being added, and the diagonal line here was removed because it was not observed any longer. So if I let this, oops, sorry. Let's just go through that again. Can show you something else. Some more cars. If we keep on going here, stop here, you can see two cars right there. Those are also cars, trust me. This is not working the way it's supposed to. Let's go back to the cars. And once we go back to this point, you see both the cars, and once the car passes, you see that those points get updated and the cars get removed from the map because they're not observed anymore. That's how the map update works. Okay, let me talk a little bit about results. So we did experiments on 30 different sequences on this parking space at different days, at different times of the day. Basically, we recorded sequences in the morning, at noon, and in the evening. And the initial mapping was done on day 1, and then all the others were used for localization on that one map. And for example, we had the scenario where we mapped at noon and then localized in the evening, but we could also localize in the morning and vice versa. And the evaluation strategy is basically we take the ground truth that we measure from the DGNSS INS system and compare that to the trajectory output from the particle filter. And also, on a side note, the lost robot problem was solved. We assumed that we knew the initial condition of the particle of the pose by around 16 meters and a 90 degrees in heading, which is basically a very rough estimate for like standard GPS in a car. Maybe a little worse, but that's just the assumption that we made. Okay, let's look at the results. So one side note about the map size. So the cluster size is about 200 kilobytes per kilometer versus 4 megabytes per kilometer if you compare that to like a standard grid mapping approach. And the mean error over all the localization sequences was about 2 meters, but that is including the lost robot convergence time that the particle needs. So in the beginning we spread the particle around 16 meters and then they just fly off in different directions. And after a certain time, they come back, and then the localization result converges to the correct answer. And and over all of this, we had a localization accuracy of 2.0 meters, plus minus about 40 centimeters in standard deviation, meaning that the localization, even though the parking lots change all the time, is always very similar. And yeah, the overall error behavior, as you can see in these two examples, are very much the same. So after a certain convergence time, the particle filter knows very well where it is, and then the localization is precise and available for use of the functions that use the localization result after it's been calculated. Okay, let me summarize what we just talked about today. So we developed a SLAM algorithm based on fast SLAM using radar and odometry sensors. The radar sensor is too noisy by itself, so we developed a cluster map representation using density-based string clustering and also incorporating the map update. And the map update enables us to robustly localize ourselves in changing environments. And that was shown on a parking lot in front of our building, actually. So future work will be, actually I teased this in the workshop on Sunday before adding more context information to the landmarks that we had with a descriptor to make the landmarks distinguishable. That will make scan matching a lot easier and a lot more and a lot more precise. And also we will be shortening the convergence time of the algorithm, maybe by better estimating our initial condition. So thank you very much for your attention, and just let me remind you to keep calm and let your car do the driving, and to join me at the poster session at 4:30. Thank you very much.
Thank you very much for your presentation. Then it's time for one question, please. If not, I have a question. There's a question, please.
Yeah.
Thank you, very nice presentation. I'd just like to ask, how can I interpret the result of mean error of 2 meters? So if I would design a control system and use the proposed system to localize my car, then my car will crash into another car by 2 meters.
Yeah, that's true. The mean error over 2 meters was basically just taking the entire trajectory from start to finish, including that bump that we saw. From the convergence, and giving the mean error over the entire sequence, and that doing for all the sequences. And actually what we were more interested in was the standard deviation, because we wanted to see if when the parking lot changes, the parking carts, the configuration changes much, if the localization result is similarly good. That's actually what we wanted to show.
Okay, thank you.
The localization result, of course, for an autonomous driving system, it's not good enough, but then we need sensor fusion and stuff like that. All right.
Thank you very much again.
The second presenter will be Michael Vlamnik from University of Ghent, who will present his work towards online mobile mapping using inhomogeneous LiDAR data.
Okay, so good afternoon everyone. My name is indeed Michiel Vlamink, and I'm a PhD researcher at the Image Processing Research Group of Ghent University. And today I will present you my work on mobile mapping using inhomogeneous LiDAR data. So this is the outline of my presentation. So as usual, I will start with a short introduction, after which I will explain the acquisition platform that we used, and the problem statement, and then I will go further to the approach that we followed, and finally I will conclude with the evaluation and conclusions. So actually the goal of this project was to design a robust and a generic system that is able to quickly obtain accurate 3D maps of large-scale environments. And the main thing is that the system, that we wanted the system to be generic in the sense that we don't want to make any assumption on the type of the scene or on the sensor setup. So here you see another result of the system. So the acquisition platform, actually we used the Velodyne HDL LiDAR scanner. I guess most of you are familiar with it. So we used the 32 version, so it means that it has 32 lasers to capture the scene. And it's continuously spinning its head at 10 Hz. So it outputs a point cloud every 100 milliseconds. And it has a horizontal field of view of 360 degrees. So, and one of the main differences between our system and most of the other systems is that we actually tilted the LiDAR scanner just to be able to create more detailed maps. And then finally, we mounted it on the mobile mapping van. So this is the van of the company Grondmee. So it's a Belgian company, a Belgian-Dutch company. And the driving speed of the van was approximately 15 kilometers per hour. So the problem statement, so we want a consistent point cloud generation using a mobile observer. So what we got, so here you can see a point cloud, which was perceived during the rotation k, or sweep k. And we have another point cloud, which was acquired during sweep k minus 1. So maybe they look quite strange, but that is because of the tilting of the sensor. So what we want is, we actually want to estimate the transformation that aligns both point clouds. And as you can see, we can assume that consecutive point clouds differ only slightly from each other, as they are captured only 100 milliseconds after one another. So actually this problem is related to the odometry problem, so the problem of estimating the trajectory of poses of a vehicle. So actually what we do is we express every point cloud in a global coordinate system, which we set at the origin of the first point cloud that was received. And then finally the reconstructed point cloud is of course a concatenation of all the separate point clouds transformed by its corresponding pose. So we made one assumption that we didn't want to use GPS just because we don't want to be dependent on it, and because sometimes the GPS signal is too weak, so we want to be independent of that. And also we performed the solution in 6 degrees of freedom. So actually we have 3 position coordinates and 3 rotation of angles. And the reason for this is that we also use the system on a drone, and a drone can also have rotation about its roll angle. So one of the main challenges of the system is that the point clouds that are generated by the Velodyne scanner do have an inhomogeneous density and are in general quite sparse. So as you can see here, so this region is quite dense because it's near the origin, so it's actually quite logical. And here the points are rather sparse, and existing methods do have problems with these kinds of data. So the approach we followed, first we will project the point clouds into a 2-dimensional grid, and after that we will perform some kind of surface analysis, and then we will do the actual alignment of the point clouds, so the actual registration, and for this we use an adapted version of the ICP algorithm, but I will explain it later on. And then finally we will also perform some kind of global registration, because we will keep or we will maintain a global map of the environment, and so we will also align the transformed point clouds with this map. And then finally we also performed some kind of loop closure, so we want to detect loops and then try to correct the error. So the 2D projection is actually a spherical projection on a cylinder. So again the same point cloud, and this gives you a view of how the projection looks like. So actually this is some kind of range image, but it also contains the 3D information, of course. So it has a height of 32 pixels, because there are 32 lasers. And the benefits of this is that using this 2-dimensional grid, we can exploit the knowledge of adjacency in the 2-dimensional domain, and this results in faster execution times. So then the surface analysis, actually this is an interdependence problem, because to analyze the underlying surface we should know, or we should define an optimal neighborhood, but the optimal neighborhood is dependent on the surface, so it's an interdependence problem. So for this we select a neighborhood, so using the two-dimensional grid. So for example we select the 8 connected neighbors. And then we still check if the points are still close to each other, even in the 3-dimensional space, of course. So after that we compute the principal components, and using this we derive some kind of feature vector, and the most important feature is the dimension of the point set. So the dimension, this means like are the points lying on a plane, or on the intersection of a plane, or do they are they more like volumetric, so representing scatters such as vegetation? And then finally we compute some kind of uncertainty measure of this. So using the Shannon entropy of a unit partition. And we will repeat this until we find the right optimal neighborhood. And using this optimal neighborhood we will derive the normal of the tangent plane to the surface. so as you can see here. And we will use this one to actually align the point clouds. So the registration, so actually we used some kind of a well-known algorithm that we adapted to our needs. So it's called the iterative closest points. So once again you have 2 point clouds, pk minus 1. So the first thing we do is we select some points on the first point cloud. So actually for this selection we base the selection on the previous feature vector. So because the points that are lying on vegetation, so the scattered points are like not very reliable, so we won't select these points. So and then we will match them with the other point cloud, pk. So just assuming the closest points criterion. So we just look for the closest points in 3D. And then we will reject the matching points if the corresponding pair is, for example, when the feature vector, for example, differs too much, then we just reject it. And then finally we do some weighting, so we incorporated robust M estimators. And then finally we minimize some kind of error metric. So this is an iterative process. So, so in one iteration the point clouds will be like this, and then we do another iteration, and then it will be finally, hopefully, like this. So regarding the minimization, so what we do is actually we try to minimize the distance between a point and the tangent plane of its corresponding point. So actually it's called the point-to-plane metric. So once we have done this local registration on 2 consecutive point clouds, we will do another registration step, but this time on a global map. But the problem is that when we add all the points together, then the point clouds becomes intractable and too large, and the denser regions become even more dense. And for that reason, we will represent the map as some kind of octree data structure. So, so an octree is like a hierarchical tree, in which for each level we will subdivide the cube into 8 subcubes of similar size. And we will resample the point cloud using this tree. So the benefits, I already said that it is hierarchical, so we can so it's online adaptive, so we can, during the algorithm, we can change the level of detail we want. And next we can, for example, at the level of at the leaf size level, we can do some filtering just by keeping only the points, or for example by replacing all the points in the leaf size by just one single point that represents the 3D centroid. And this leads to a homogeneous density of the global map. And this leads to faster execution times and more accurate pose estimates, of course, and very few drift. So actually this system is working like this, but we also incorporated loop closure. So once we detect a loop, we will try to correct for the drift, because the SLAM algorithm is of course inherently to drift. So this here is a pose graph of the poses of the trajectory, and you can see here, so we have, for example, found that these 2 poses are actually representing the same space, or the same position, I mean. So the first thing we do is actually we try to identify the difference in pose, so the delta, the error, and we try to propagate this error back into the pose graph. So for this we just assign each edge some kind of weight, and this weight is actually based on the residual of the minimization step of the previous submodule. And the idea is that when there is a high residual, then we assume that the clouds were not really accurately aligned. And then we finally update the translation and the rotation separately. So the slurp means spherical linear interpolation, and so the translation we just multiply with the weight factor. Okay, so now the evaluation of our system. So actually we recorded some sequences in the Belgian city of Hasselt. And together with the Velodyne LiDAR data, we also acquired the ground truth information using this POS-LV system. So it's a GPS system and also GNSS system, which includes EMU data as well. So as you can see, so these are 2 results. So I plotted the path on the 2-dimensional plane, on the ground plane. So as you can see, the ground truth and my result are quite accurately lying on each other. So you see here for the loop closure that there is a little difference here, but still without the loop closure, it's more or less, well, not really the same, but it's close. But now the numbers. So actually, we use the same metric as they do in the Kitty benchmark. So actually, I subdivided the total length of the sequence into sublengths of 200 or 300 meters and so on. And actually, the result we obtained was like we have 1.4% of average translation error. And regarding to the rotation error, it converges to 8,000 degree per meter. So actually this is more or less comparable with the results people got on the Kitty benchmark, so the top 10 people of that benchmark. And regarding the speed, we have to say that of course it depends on some parameters. So for example, the size of the global map or the leaf size. But for a leaf size of 5 centimeters and some kind of subset of the map, we can reach 10 frames per second. So actually this result was actually using this leaf size of 5 centimeters and using some kind of bounding box for the map. So this slide shows you some example of the 3D point cloud more in detail, because this one is probably not that clear. So here you can see the Google image of the point cloud. And maybe I can also show you a video how this works. Okay, so here you see the car driving, and yeah, it's mapping its environment as it should be. But I have to say that I speeded this up 4 times, just to be saving some time, otherwise. So this is using a leaf size for the global map of 5 centimeters. So it's running at 10 Hertz. Okay, but I think I should go on, so if there are further questions you can still ask me. So, the conclusion, so actually we succeeded at designing a robust system. So it copes with the inhomogeneity of the data using the surface analysis and maintaining the global map. It's generic because we do not assume any semantics of the environment, so we do not assume that the ground plane is visible, for example. And it's large scale because it copes with drift using the global map, but also because of our loop closure algorithm. And it's adaptive, so the speed and the accuracy can be adapted because of the hierarchical representation of the map. But it's always a trade-off between accuracy and speed. So thank you for your attention. So if there are any questions, feel free to ask.
We have time for one question.
Hi. Over here in the front.
Okay, I see.
Hi. Just a question. When you're doing this mapping, do you need to have all the data be taken consecutively, or could you presumably mix data from different data collections?
Well, I assume that data is indeed consecutive.
Right.
Yes. Because that's the meaning of the online word in the title of my presentation. So online means that it copes with newly arrived data. So,
okay.
Yes.
Okay.
Okay, let's thank Michael once more.
Yeah.
Okay, the next presentation is of Thomas Martinez Marin from University of Alicante. The title of presentation is a compact representation of the environment and its frontiers for autonomous vehicles navigation.
Thank you for the presentation. My name is Tomás Martinez, and I'm going to present a new algorithm of SLAM. The name is contour-based SLAM, and I'm going to give you a short description of the algorithm, and then I'm going to show some experimental results with videos and the conclusions. Well, the main motivation of this work is to convert conventional vehicles, like this golf cart, in autonomous vehicles for industrial applications. So it's very important to create maps and for localization and for navigation. So the map can be, usually is occupancy grid maps, is very popular solution, but we present another alternative SLAM that has some benefits compared with grid maps. For example, scalability. Here we have, sorry. Yes, here we have a grid map, and here we have a contour map. So we present the benefit of the scalability because we require almost 3 orders of magnitude less memory. It's able to represent unstructured environments, and also we present a new concept of frontiers, that we close the area of the map to separate the free space with the unknown space. So this mapping is based in contours. Contours is defined by a sequence of ordered and weighted data points. So it's a polyline. It's a polyline with weights. The weight represents the probability that in some point there is a physical object in that point. Okay? So the object can grow, can merge, can split, can disappear. And we implement a resampling mechanism that is physical, with the sensor is close to an object, with resampling the point, the data points, and also computational. We use the Douglas-Pecker algorithm to remove the redundant points. Also, we use a new concept of frontiers that is important in this case because we want to use for motion planning, to use reinforcement learning, and in polylines algorithms, they don't represent the frontiers, and in this case, the frontier is a virtual contour that closes the explored space. So inside the explored space, we have the free space, and outside we have the unknown space. So this is quite useful for motion planning. Here we present more or less the algorithm. We have implemented a state machine with main 4 states. So when we get the laser scan, we segment the laser scan in contours, and we update the contours in the map with the contours in the laser scan. So with this state machine, we can update, merge, insert, and remove contours. So in the poster session, I can explain in details. For localization, we use an ICP algorithm, but it's a variant of ICP algorithm because we use the weight that are in the contour. So, for example, a building has a weight that is higher than a bush or a person or a mobile object, for example. Also, we address the problem of loop closure and map optimization. We follow the ADLAT approach. So in large environment, we create submaps, and we detect the loop closing using also contours. In this way, here, here we compare the contour of the laser scan with the contour in the map, and we generate some rototranslation with some hypotheses until we fix the best solution. And finally, we use the map optimization in the case that we have problem with the local closing. Now I'm going to present some results. First in dataset. For example, here a very conventional dataset is Intel Research Lab. Here we have the result with grid map, the mapping. And here we have our results, where in red we have the contours that can describe any shape, and also the frontiers here in black. And here we show a detail of the object in colors. So the result is quite similar to grid map. Here we have another data set, Access Building, and the result is similar. Here we have a grid map, and here we have contours. You can see in colors the different contours, and inside the area, the explored area, is in black, is free space, and outside in gray is unknown space. So we use a metric, a conventional metric assessment for this kind of maps, two-dimensional maps, and we can see, compared with another techniques, scan matching, ICP, and RBPF, particle filter, graph mapping, and we can see that the results are similar in the case of this approach, even better in some cases, but the memory is quite different, because here with precise grid map you can have, you need about 1.5 gigabytes, or maybe you use 15 particles, you can have 500 megabytes. And in our case, we only use 0.1 megabytes to save the same map with the same capability to motion planning. And here, with Access, we have more or less the same solution. So we have about 3 orders of magnitude less memory. We need less memory. So we get the scalability. Now I have a problem with the video. I'm going to show the video outside the presentation. Here we have a video. So it's not I should have to change. We have to start again. Here is the Intel Research Lab, where we put some artificial error to show the loop closing and map optimization. So you see how it's creating the map. You see the scan, laser scan, and how when there's some problem, then the optimization map algorithm fix the zoom map. So here we can see. But usually we only need one map in this case, but it's only for illustration of the result. Another one. Also, I need to put yes. No, it's not. This one. Sorry. Also, we have checked this algorithm in a experimental platform, the golf car, in a special area in the campus of Alicante, and we can see how the vehicle can avoid people and is located with the contour-based SLAM all the time. We have checked it, for example, here we don't. The vehicle cannot follow the trajectory because it has a problem with the wheels, and anyway it can be located in the environment with bushes, with a fence, with another kind of elements and go to some position, then go to another position, and finally return to home. In this case, we combine this SLAM algorithm with optimal path planning with reinforcement learning in two layers. And we have a local reinforcement learning and a global reinforcement learning algorithm in the upper layer. So we can see how the precision is very good. We don't use GPS. Here, the car goes to the pallet. High precision. And then go home again. So we can see that it's quite precise. Now return to the initial position. Here we have checked it with a lot of people moving around, and it's quite reliable. So, okay. So finally, we have experiment in the main campus of University of Alicante. We got this map is 100,000 square meters. We represent in red the main buildings and in green the bushes and trees. So we can see here that is very can fit very good with the Google Map, Google Image in this area. So we saw scalability. This map, the size is about 0.5 megabytes. It's 100,000 square meters. So conclusion, finally, if I have time, I have an extra video. If I don't know, I have time. So conclusion, we propose a new contour-based SLAM that is an online algorithm for indoor and outdoor large environments. The contours can represent any arbitrary object obstacle, and it adopts the scalability. For example, we can represent the whole campus of University of Alicante, that is 75 hectares, with the memory of just one picture, 5 megabytes. We present the new concept of frontiers to close the explored area, so we don't need to represent the free space. Also, we provide some higher level of abstraction because we work with contours, not just with cells. Our future work is to extend this approach to 3 dimensions for laser scanner and image sensor, and also to use this approach for dynamic environment using this level of abstraction. Can I run the video?
You have 1 minute.
So we check in the main campus, we check the navigation capability. Here we can see the contour-based mapping, and it's not very good synchronized. And here we see the vehicle, and there is a person here that is in front of the car, and you can see how is the localization. And the car avoid the person here and remain located. And also here we have another obstacles that is represented here, and we have this avoid the obstacles, and here we have an area without map, but the car can recover and finally can avoid that obstacle. So, thank you very much for your attention. I finish now.
Thank you very much. If there are questions, please. There you go. Do you have a question? No? No. Okay. So I have a question. Please tell us what happens when the size of the space is growing,
Yes.
and the loop closure doesn't appear.
Doesn't appear.
Yes.
When the size is growing, the explored area is growing, and you can accumulate some small errors until you get a load closure, and then you can solve the problem and fixing the submap. But usually in this area, and usually in indoor environment, we don't have problem with loop closure, only with big maps. But in this case, we use submaps of 40 meters. So it's enough to solve the problem.
Okay. Other questions? If not, thank you very much.
So the last presentation for the session is Hendrik Königshoff from FZI, who will present vehicle localization with tightly coupled GNSS and visual odometry.
Welcome to my presentation about vehicle localization with tightly coupled GNSS and visual odometry. My name is Hendrik Königshoff and my co-authors are Markus Schreiber, André Marcel-Helmut and Christoph Stiller. First I will come to our motivation. For map-based autonomous driving, exact precisioning and accurate localization is a key task, and usually therefore high-precision integrated navigation systems are used. But these systems have the disadvantages of high costs and inaccurate rate localization in GNSS-denied environments. That's why we investigated which results we can achieve with low-cost sensoric, and we used a GNSS receiver and 2 cameras in a stereo setup, which were cheaper than the integrated navigation system, and our goal was a lane-accurate localization. First I will tell some words about the algorithm, then I will come to the evaluation results, and I finish with the conclusion. The algorithm. Here on the right side you can see the basic principle of GNSS positioning. With a time delay of the signal between the receiver and the satellites and the speed of light, you can calculate so-called pseudo-ranges, which are the pseudo distance between the receiver and the satellite, and equals the real distance added by a receiver clock error and further measurement errors. And 4 pseudo-ranges are necessary to calculate the receiver precision. A further parameter you can achieve from GNSS receiver is the delta range, which is the frequency offset between the transmitted and received signal due to this Doppler offset. Now there are two main approaches how you can incorporate the measurements of the GNSS receiver. One is a loosely coupled one where you incorporate GNSS precision and velocity measurements, and another one is a tightly coupled approach where you directly incorporate pseudo and delta range measurements. And this approach has the advantage that you can support the visual odometry, in our case, even in the case of lower than 4 satellites available. For the fusion of the GNSS and visual odometry, we used an extended Kalman filter with the state vector. And besides the precision, velocity and orientation of the vehicle, we had to estimate a receiver clock error and drift because of the tightly coupled approach. And we initialize our system by the first GNSS measurement as soon as the car is in motion. And with a pseudo range, we can calculate initial precision and receiver clock error with the delta range, initial velocity and receiver clock error drift. And with the velocity, we calculate initial orientation. The next step is that the system proves if new visual odometry data is available. That means if a new stereo image is taken, and the stereo image is taken with 10 Hz. After that, the future points between both images and the previous stereo images are detected, described and matched to calculate a 6-degree of freedom motion estimation, which resulting in 3 translation parameters and 3 rotation parameters. The translation parameters can be used as estimation of the velocity with a time between 2 frames at the estimation step, but the rotation parameters has to be handled as known input since their derivatives are not considered in the state vector. The covariances of the translation parameters and rotation parameters are estimated by an error propagation of the reprojection error. If no new visual odometry data is available, there's only a prediction to the next time step. After that, the system checks if new GNSS data is available. The GNSS data rate is 1 Hz in this case. And we propose a sequential processing of the pseudo and delta range. That means given n pseudo ranges at one time, we are doing n estimation steps successively. And the advantage of this approach is that the measurement error, that the measurement vector has the same size from time to time, and the inversion of the Kalman matrix simplifies to a simply division. The covariance of the pseudo and delta range are estimated by the signal to noise ratio of the respective satellites. And after the estimation steps of the pseudo range, the solution validation is done to detect measurement errors like multipath reception. And in the case of at least 4 delta ranges, correction of the orientation is done by the velocity in the navigation frame. Here you can see a flow chart of the whole system. And this approach has the advantage that not only different data rates, as we used 1 Hz and 10 Hz, but also different validity times of both sensors can be considered. Now I will come to the evaluation results. We recorded different data sets with different GNSS reception conditions in Karlsruhe. And all data sets have in common that ground truth data isn't available because of the mentioned problems with the integrated navigation system. And that's why we plotted the results on a map in order to evaluate them qualitatively. Here, the route of our first test track is shown, where the first part of the route has open sky scenarios, so a lot of satellites are visible and the positioning can be calculated very accurate, but the rest of the route is the vehicle drives through inner city areas with buildings on both sides of the route. And so the number of visible satellites are under 4 for most of the time. Here we can see the calculated trajectory by the integrated navigation system and the number of received satellite signals. So in dark blue there are the parts with lower than 4 satellites, and in red there are up to 16 satellites visible. And as you can see, especially at 2 parts of the route, the precision estimate of the integrated navigation system differs tremendously from the real position because of lower than 4 satellites are available, and that's why the precision estimate is solely based on the inertial sensors, and due to the sensor drift this measurement is affected by a measurement error which grows quadratically with time. Here's another plot to show the bad GNSS reception conditions. These are the localization results of our low-cost receiver. In blue you can see the position as a localization with GPS end cloners, and in black there are the localizations using only GPS. And as you can see, apart from this part of the route, the localization using GPS is almost impossible, and even with a combined usage of GPS and cloners. And there are parts of up to 200 meters where where less than 4 satellites are available. And especially in the case of 4 satellites with a combined usage of GPS and cloners, there are some measurement errors because of the different UTC times used for both systems. Here the great advantage of our system is shown, as we can enable a continuous accurate localization even during parts with longer GNSS signal outages, and in addition we are robust against the mentioned errors from the GNSS positioning. And the system outperforms the integrated GNSS INS navigation system, especially in the mentioned 2 parts, where the integrated navigation system is solely based on the inertial sensors. And the better results of our system comes on one hand from the tightly coupled approach, and on the other hand from the lower drift of the visual odometry against inertial sensors. And to make the improvement through using the tightly coupled approach more clear, here's another data set where we artificially reduce the number of visible satellites to 3 or less. And here you can see a ground truth in yellow, this is a manual ground truth. The tightly coupled positioning in purple and the loosely coupled in green. And here the position error of the tightly coupled and loosely coupled one. And as you can see, because the loosely coupled approach is solely based on visual odometry in the parts with less than 4 satellites, here the blue crosses we allowed the whole number of satellites to show what happens if there are all satellites available and there's a correction of the loosely coupled positioning. And the tightly coupled approach can use the remaining satellites to support the position estimate, and therefore the position error is tremendously lower than the position error of the loosely coupled approach. The position error of the tightly coupled approach is dependent on the number of visible satellites, so up to 3, and the satellite constellation, and that's advantages if the satellites are in 90 degrees to each other, referring to this receiver. And in addition, it's advantages if the visible satellites switch from time to time, which is not uncommon in urban areas where the buildings on both sides of the road were deteriorating the GNSS reception, and so the direction of the route you are driving is responsible for which satellites you see. So every time you switch the direction, the satellites are switching. And as you can see here, also in our approach, the tightly coupled precision error decreases every time when a satellite switched. Now I will come to my conclusion. We described a fusion algorithm for fusing GNSS measurements and visual odometry, and enabled a lane-accurate localization in inner city areas. And due to our tightly coupled approach, the the drift in GNSS-denied environments is decreasing, and even with the used low-cost sensors, we outperform the integrated navigation system. Thank you for your attention.
Any questions?
Yes.
Thank you for the presentation. It is, I have a lot of trouble to understand what will be the contribution, because we all know that if you use the information from each satellite, you maximize the information with respect to the standard solution. And then when you want to compare the fusion with the vision, with inertia, there are many other factors that you have to consider, like how calibrated and aligned are the inertial sensors, and also the obvious question that you may ask is that if you include an encoder and a gyro, that you could get a much better result than the integration with vision. So perhaps if you can summarize what is the contribution, so we can make, I can understand better what you're trying to infer from your presentation. No?
So you mean a wheel encoder has better results than...
what I'm saying is that it's very hard to say that vision plus using the pseudo range is with this you can get a better result with other fusion like vision, like encoders and inertia. So we'd like to know why you consider that with vision and pseudo range you can get better result than with other combinations. No?
Yeah, we wanted to test which results we can achieve with solely using GNSS and visual odometry. But you are right, if you are using more sensors like a wheel encoder and an IMU2, the results would be better. So, but the aim of our work was to use only low-cost sensors. So.
Okay, any more questions? Yeah, the one over there.
Can you tell us the maximum error of this localization system and the average errors, or for example, 1 meter coverage of during the whole trip? And another thing is, in the trip, there are many times there were only 2 visible satellites. Does this signal really help the localization, or it may bring some damage to this kind of tightly incorporation?
Yeah, the 2 remaining satellites can help that the drift of the visual odometry is decreased. And to your first question, the average error longitudinal was 1.7 meters and lateral 2.5 meters, I think. And these precision errors are not accurate enough to drive autonomously, but it's a good basis for further sensors fused in this fusing so that you can enable accurate localization. Is this answering your question? Or?
I think we have to wrap up there. So I think we should thank the presenters of these sessions again.
Okay, at the end of the session, I would like to express my gratitude to the presenters and authors, and also to thank you for your presence. Thank you.